So today we have Dr. Charles Hohensee from the University of Delaware. He received his PhD in Mathematics and Science Education from San Diego State University in 2011. And prior to his graduate studies, he was a mathematics teacher at San Diego, Los Angeles, and Vancouver, Canada. He completed his teacher training at Simon Fraser University. He is currently an associate professor at University of Delaware, where he teaches math content courses for prospective elementary and middle school teachers and research theory courses for mathematics education, PhD and EDD students. He's also interested in the second year of an NSF career grant looking at backward transfer. So let's welcome him, and now we turn the time.
Thank you, Jill. Thank you very much for inviting me to come and talk about my favorite topic, backward transfer. So what I thought I would do is start out by giving you a visual representation or a visual picture of how I think about backward transfer, and then move towards giving you a definition. So just imagine that you're a learner like this person here, and you encounter a concept. So we'll imagine that this is a mathematics concept, so it's maybe a problem or some kind of activity that you're working on. As you think or explore that concept, you're going to develop some knowledge, some understanding, some ways of reasoning about that concept. And let's call that concept one to kind of distinguish it from another concept. So imagine that you now encounter a second concept, concept two, and what might happen as you think about that concept is you might develop, or you might use your ways of reasoning about concept one to influence how you think about concept two. And that arrow kind of represents that influence. And that's transfer. That's how we define transfer of learning. But what I'm interested in is the reverse direction. So in other words, what happens to your ways of reasoning about concept one as you think about concept two? Does it change in any way? And I call that reverse direction backward transfer. So now I'm going to give you a definition of how I think about transfer, but I'm going to do it in three stages. I'm going to first give you a couple definitions that I build from. So first I'm just going to give you the traditional definition of transfer. This is the way that transfer is typically defined, just like regular transfer. Transfer is the study of how knowledge acquired in one situation applies or fails to apply to another situation. And the reason people think about this as being from the expert's perspective is because typically you're only given credit for transferring your knowledge if you do it correctly. So the expert decides what's correct or not correct. So that's from the expert's perspective. Some people have criticized that perspective because they think that we don't just transfer our knowledge in normative ways, we also do it in all sorts of idiosyncratic ways. And so Lovato defines it in a more encompassing way. She says, transfer is the influence of a learner's prior activities on his or her activity in novel situations. And when she says the word influence, she means any kind of influence. It doesn't have to be something that leads to correct performance. And because of that, this is taking the actor's perspective. If there's some influence, then she would count that as transfer. But we're still talking about regular forward transfer. What I did is I took that definition and I extended it to backward transfer. So my definition of backward transfer is it's the influence that learning something new has on a learner's prior ways of reasoning about a different or related concept. And I'm using the same word influence because I would count any influence from new learning or concept two on someone's prior ways of reasoning about concept one. As I would count that as backward transfer. Let me give you some examples some empirical examples that illustrate what backward transfer is. And the first example comes from a non-math context. There's a lot of research out there, linguistics research or language learner research, about how when you learn your second language, if you're a bilingual speaker, you no longer produce or comprehend your first language quite the same way. So let's say you learn a new language and then you go back home and talk to your parents. Your parents might notice that you say words a little differently than you used to. And they call that backward transfer. And that's been well shown. In mathematics education, it's not as common. But there are findings that I think are instances of backward transfer. Like McGregor and Stacy, they have a study on algebra symbols. And so, for instance, if they showed that when students learn about concept 1, which is algebra symbols without exponents, and then learn about algebra symbols with exponents, they subsequently become more confused about algebra symbols without exponents. Like they might think that 3x means x to the third. Another example comes from Van Duren et al. They did a study where they taught students about proportional relationships. That was concept 1. Then they taught them about non-proportional relationships. And they found that after that, students started getting confused about proportional relationships. So I consider that a case of backward transfer. This is an interesting study from Piaget. He showed 3-year-old children an arrangement of sticks going from large to small or small to large. And then a week later, he asked the children to draw the sticks. And so these 3-year-old children typically drew some sticks, but they would draw them all the same length. So that's concept 1. They're an image of what that spatial arrangement looks like. Then he waited 6 months, and in the intervening time, concept 2 is basically the child going through life, exploring different size objects. And then he said to the children, remember when I showed you those sticks 6 months ago? Can you draw them again? And after that, the children started drawing more nuanced versions of those sticks. They didn't draw them all necessarily getting smaller and smaller, but they did show some big sticks and some small sticks. And so Piaget said that their prior ways of reasoning had been changed because of all the activities they had. Their mental schemes about spatial arrangements had become more advanced. And so their memories, in a sense, actually got better over time. And here's one more from Ferenc Martin. He looks at differences, when you notice differences. So let me give you an example. So if you would show someone a red billiard ball, say that's concept 1, and then take away that red billiard ball, they would have a certain way of reasoning or thinking about that billiard ball, that certain things would be foregrounded, certain things would be in the background. If you showed them a white billiard ball, subsequently, their memories of the red billiard ball might have changed because the redness of the billiard ball becomes more salient, comes to the foreground, comparing it to the white billiard ball. Or, for instance, if you showed them an egg after showing them the red billiard ball, the roundness of the red billiard ball might come more to the foreground when thinking about the white billiard ball. So when you see something different for concept 1, sometimes that can help you foreground something of concept 2, and then that can help you foreground something different about concept 1. And then finally, here's an example from something that I did. I talked to teachers, and one teacher said that she noticed when students learned about metric conversions after they learned about scientific notation, this is in the science class, their understandings or their ways of reasoning about scientific notation now got a little more confused because they were kind of, the metric conversions ways of reasoning was interfering. So those are some examples to help you think about this. Now I want to just kind of share how I'm conceptualizing this. So I've got a picture here of a brain. I mean more like think about the mind. But first I want to read you a quote from a famous article from Misconceptions, called Misconceptions Reconceived, Smith, DeSessa, and Rochelle. And in that article, they say that overall, learning a domain of elementary mathematics for science may entail changes of massive scope. New elements may gradually come to play central roles as core knowledge, creating very large ripple effects through the system. And that last part is the part I want to focus on, because I think very large ripple effects could refer to something like backward transfer. So for example, imagine, this is a metaphor, but imagine you learn something, but that blue dot, let's just imagine that that's the new learning that's taking place in your mind. What I'm thinking of with backward transfer is that it could be kind of this ripple effect out through the cognitive system, that as you learn something new, it can influence other cognitive systems that are in your mind. A couple other points about my conceptualization. This is based on the idea that there's a two-way relationship between prior knowledge and new learning. And that's a little different than most of the research, which mostly looks at how prior knowledge influences new learning, how you can build on your prior knowledge. And there's very little research that looks at the other direction. But I personally think that there's a two-way direction. And then another idea that I think is important for how I'm thinking about it is this idea of conceptual distance. For me, in order for backward transfer to be interesting, the conceptual distance between concept 1 and concept 2 has to be not too close. Barnett and Ceci they distinguish between near transfer and far transfer. So I'm thinking more along the lines of far transfer. If the concept 1 and concept 2 are too close, then it's really, you're kind of really just mixing, it's really just one concept. And when you learn concept 2, you're really just also learning more about concept 1. It doesn't feel very transfery to me. So what I'm interested in is where concept 1 and concept 2 have some conceptual distance apart, so that there's more of an interesting effect there. Hopefully that makes sense. Okay, so I have a couple of criteria that I think might be important. One of them is that I think there are certain ways of reasoning that are more susceptible to backward transfer. And I mean susceptible in not a negative way, but could be positive or negative. So for instance, I found that depending on what you focus on, either quantitative reasoning or numerical reasoning, when you're teaching concept 2, that can influence how students think about concept 1. So if you really emphasize quantitative reasoning in concept 2, there's a chance that students might think more quantitatively in concept 1. I also showed that the levels of covariational reasoning, the way that students reason covariationally, can change. If you teach concept 2 in a way that emphasizes higher levels of covariation, then there's a chance that students will reason with higher levels of covariation in concept 1. And then I have a couple more hypotheses that I have not shown yet, but I think that this distinction between a covariational view of functions or a correspondence view of functions could be another way of reasoning that might be susceptible to backward transfer. And then finally, there's also a distinction between an action view and a process view of functions, and I think that distinction could be susceptible. And I will say more about that last one because I have some new findings to show a little later on. And I'll explain a little more about that distinction if you haven't heard about it before. Okay, I also think there's certain criteria that I have for certain math concepts that I think are more susceptible. Like for instance, I think that in order for you to have backward transfer, the two math concepts should be connected by some way of reasoning. If the concepts are too different, I mean, I think any two math concepts are connected, but if there's not a strong way of reasoning that connects the two concepts, then I probably would think that you might not notice a backward transfer effect. Also, the instruction for the two concepts should occur relatively close together for you to notice a backward transfer effect, I think. And of course, it's the one that's taught first. That would be the one that would be the susceptible one. If they were taught too far apart, especially for students who are not really metacognitive, you might not see much of a backward transfer effect. Also, I think there's a trade-off. I think the farther apart conceptually two concepts are, the weaker the backward transfer effect. If they're very different concepts, it's going to be hard for there to be a strong effect. But, like I said before, the farther the concepts are apart, the more interesting or impressive backward transfer is. So I think there's a bit of a trade-off. We want concepts that are far enough apart that you're going to see effect, but not too far apart that you're not going to see effect. So that's kind of the game that I'm trying to navigate. And then here's a couple of examples that I showed that linear and quadratic functions are kind of a nice distance apart. They're not too close together, but there's potential there for backward transfer effect. One of my grad students showed that derivatives or differentiation and integration, that's a nice distance apart that you can see an effect. A teacher said that with their students, distance time graphs and then speed time graphs are another context where you might see backward transfer. Why would you want to study backward transfer? Maybe it's an interesting phenomena, but what would be the reason to actually study it? Well, here's a couple of reasons. First of all, if there's such a thing as productive backward transfer, and I haven't talked about productive or unproductive too much yet, but if you had a backward transfer effect that actually made thinking about concept one better, then that would be something the field would want to know, because that's some untapped potential. We could get teachers to do more of that, and then we would get this extra productive effect. And on the flip side, if there's such a thing as unproductive backward transfer, in other words, students get more confused about concept one after learning concept two, we want to know that too, because we want to limit that. We want to minimize that. We would want to help teachers not do that, because that's impeding students' conceptual development. Okay, I'm going to talk now a little bit about my research. And first of all, I just want to kind of walk you through a couple of the things that I've done and kind of give you a perspective of what I've done so far. So I started with a teaching experiment because I wanted to see if I could produce productive backward transfer, a proof of concept. So I worked with a few students and was able to show that students' ways of reasoning about concept one, I thought, improved or became more productive after I taught them about concept two. So that was like the first foray into this. Then I was kind of interested in what was happening in classrooms. So I interviewed teachers to see if they were observing anything. When they're teaching, do they ever observe that students' conceptions of concept one change? And in a number of cases, I got some new ideas like the scientific notation, metric conversions, concept one, concept two. Teachers were aware that there were times when they taught something where their students got more confused, or I think it was mostly more confused that they noticed about something happened to concept one. The next thing that I did, and this kind of brings us up to my current research, some grad students and I wanted to go into classrooms ourselves and see what was happening. So over the past year, we conducted an observational study where we went into classrooms, and I'll explain a little bit more about this, but we wanted to see, was there some effect that was happening that we could actually measure or observe and investigate. And then finally, this takes us beyond what we've done so far. Our next step is going to go and do another teaching experiment, but this time we're going to take the materials that we started to develop at the very beginning and refine those, and then also bring teachers in to see if they can use our materials to get the same effect that we're getting. Okay, so now I want to go back to the third one, which is the one that we're currently working on, and give you a little bit of a glimpse into a few of our findings. One of the research questions that was guiding this was, in what ways do students in real classrooms, prior ways of reasoning about linear functions change, if at all, along the dimension of an action versus a process view of functions, after they participate in an instructional unit on quadratic functions? So I'm going to explain first the methods for this. Our participants were Students from 2 urban high schools that drew from low SES populations. And we had 1 class per school, and both classes were teaching integrated mathematics 2, and the classrooms were made up of 9th and 10th grade students. One teacher, Ms. Henry, she had 24 students, and it took her 16 lessons to teach the entire quadratics unit, and all 24 students agreed to participate. The other school, Mr. Anderson's class, had 33 students. All the students agreed to participate, and he used 12 lessons to teach the quadratics unit. And the 2 units were between 4 and 5 weeks each. Ms. Henry had 8 years teaching experience. Mr. Anderson had 17 years teaching experience. And interestingly, even though the teachers were both teaching IM2, neither of them used the curriculum. So they just made up their own materials. And we didn't tell them what to do. We just said we just want to watch. And so they would just get worksheets off the internet or make up problems off the top of their head. But they were, I'll show you later, they were actually good teachers, but that was an interesting feature that there was no curriculum that I saw evidence of at all. And then we had a pre-post design. So before the quadratics unit, we gave all the students a linear functions pre-assessment, and we interviewed 4 students per class about their responses on the pre-assessment. Then students participated in their quadratic functions unit 4 to 5 weeks. We didn't tell the teacher what to do, they just did whatever they wanted. And then we gave them a post-assessment. The pre and the post-assessment we had 2 versions of the assessment, and so half the students took version A for the pre-assessment and version B for the post-assessment, and then the other half of the students did the opposite. And the assessments were, they were the same structure, the same type of problems, but the numbers and the context had been changed a little bit. And then we also interviewed the same 4 students about their post-assessment responses as we had in the pre-assessment. Okay, and then in terms of analysis, we started by analyzing the pre and post assessments. So we developed a coding scheme for the assessments, and we used a priori codes that we found in the math ed literature. And then where those didn't fully account for what we were seeing, we also developed some induced codes. And we refined the codes using a constant comparison approach. So as we were coding, we continually refined our coding scheme. Our unit of analysis was a problem part. So the assessments had various problems, and each problem had parts, and so each part got a code. We addressed intercoder reliability by always having 2 people from our 3-people research team code each part, and then they would code them independently, and then they would meet, and they would compare, and then when there was any differences, they would resolve differences. After we coded all the data, we tallied instances of each code by student and also by problem part. And in those tallies, we started to look for, were there any patterns in how students' reasoning was changing? And we also analyzed the quadratics units. Basically, we just looked at what were the main quadratics foci for each of the lessons. And then we compared the coding of the lessons with the patterns of any changes in reasoning. We were looking for, were there any conceptual connections between those 2 sets of analyses? So, as I said, Ms. Henry and Mr. Anderson were actually good teachers. They had some similarities and they had some differences. Some of the good similarities were that the teachers were very well liked. The students were held accountable to participate. They were all very cooperative. So these were well-run classes. But on the negative side, the teachers were the sole authority in the classroom. They asked very closed-ended questions. And also, in terms of quadratics, one thing that we think is important is that data points for quadratics were always generated by using an equation, substituting into an equation. That was the only way that they ever generated data points. And I'll say a little bit more about that in a minute. And then some differences is that Ms. Henry focused a lot on graphing and factoring, but not factoring for the purpose of solving, just for the purpose of factoring only. And there was quite a bit less focus on actually solving, say, for the roots of the equation. Mr. Anderson, in contrast, had much less of a focus on graphing and on factoring when it didn't involve solving. So, and his main focus was on a lot of solving, trying to use the quadratic formula, trying to complete the square and solve, trying to factor to solve, etc. And our main claim is that we think that some students' view of linear functions along this distinction between an action view and a process view of functions appears to have been influenced by the quadratic functions instruction. And so here's where I'll just briefly explain the distinction between an action view and a process view. So from an action view of functions, you would think about a function as being basically the calculational steps to get an answer. So it's basically just a calculation. You could do the steps repeatedly, that's fine, but the steps aren't really seen as being connected in any way. It's just you're just calculating steps or calculating an answer. In contrast, a process view is a much more holistic view of the function. You're conceiving of all the inputs, you're conceiving of all the outputs, and you're conceiving of the relationship between the two, all in your mind. That's all part of your conception of what a function is. So it's a much more comprehensive or holistic view of what a function is. Okay, so I'm going to share with you two subclaims that support, we think, our main claim, and they both have to do with a problem that was presented pictorially. So on one version of the test, students were given a story about a plant that's growing at a constant rate, and on the right, or on the other version, they were given a story about a container that was filling with rainwater at a constant rate. And for this first part, this first subclaim I'm going to show you, students were asked these questions. Explain how to find the height of the plant on day 17, and explain how to find the total amount of rainwater if the storm lasts for 11 hours. So students often did things differently on the pre-assessment than they did on the post-assessment. So let me give you an example. Oh, let me first say what the claim is. So some students changed their way of reasoning in terms of using, in Caput and West call one way, a build-up process, or they use what they call an abbreviated build-up process. So here's an example. This student, on their pre-assessment, they were asked about the rainwater problem. And so to find the 11th hour of rainwater, you can see that they're keeping track of the hours, and every hour they're adding 4 centimeters of rainwater until they get to 11 hours. Caput and West call that a build-up process because you're building up to the answer. And I think what's important here is you're kind of doing this one step at a time, one after another. Versus on the post-assessment, the student used an equation. They multiplied they were doing this as a plan example, so day 17. They multiplied 17 by 2, which the plant grows 2 inches every day. They didn't deal with the y-intercept correctly. They got that incorrect. But the process of going straight by multiplying rather than building up is what Caput and West called a abbreviated build-up process. Interestingly, this one you could think about as being a little less sophisticated than this one, but because of the y-intercept, having to deal with the y-intercept, a lot of students got this wrong versus when they used the build-up process, they got it right. So is this a productive change or unproductive? It's kind of mixed, especially in this student's case. Okay, so here's what happened in the two classes. So for Miss Henry's class, 23 of her 24 students showed us a sufficient response that we could tell if there was a change or not. And for Mr. Anderson, it was a little less. 20 of his 33 students, they gave us a sufficient response that we could tell if it was a change or not. And for Miss Henry, 6 of her students changed from a build-up process to an abbreviated process. So 6 of the 23. Versus for Mr. Anderson, 7 of the 20 students changed from a build-up to an abbreviated build-up. So going from one step at a time to then doing it kind of all at once. But there were also students who went the other way. There were students who changed from an abbreviated build-up to a build-up process. And for Ms. Henry's class, that was 3 of the students. They went the other way. And for Mr. Anderson's students, 2 of the students went the other way. So more students went from build-up to abbreviated build-up, but there were students that went the other way. Well, what's our interpretation with those findings? Well, one thing we think is that if you would go from a build-up to an abbreviated build-up, we think that could indicate a possible shift in the direction of a process view from an action view. Because you're no longer doing like one step at a time, like you don't have to do that, but you can realize more holistically that each day it's going to grow the same amount, and so you can kind of do it all in one step. Another interpretation would be that they're going from an additive reasoning to multiplicative reasoning. That could be another way to think about this. Or another way would be you're going from covariational reasoning to correspondence view reasoning. And our hypothesis for why this happened is that we think that the fact that none of the lessons ever had students reasoning about building up, I think that might have drawn students' attention away from using that approach. So in other words, thinking about like what will be next, the next step, and the next step, and the next step in a quadratic function context. Okay, I've got one more subplane to share with you. This is again to do with the same problem, but on another part of this problem, they were asked a different question. So for this part of the problem, for the plant, they were told, you have to leave the plant in your office over the weekend. You did not measure the plant for 2.5 days. The plant grows at the same rate the whole time. How much did the plant grow in the 2.5 days you were gone? And then for the rainwater problem, we asked them, where we told them, you fall asleep while watching TV. You did not measure the rainwater for 3.5 hours. It rained the whole time at the same rate. How much rainwater was collected during the 3.5 hours that you were sleeping? And you'll notice there that we're not saying a particular 2.5 days or a particular 3.5 hours, but it's any general interval of 2.5 days or 3.5 hours. And the subplane is that some students changed their way of reasoning about a specific value of the independent variable or a general interval of a specific size of the independent variable. And the important thing there is specific value versus a general interval. So here's what happened. So this student was asked about the plant on the pre-interview. And what they did is they multiplied the 2.5 days by 2, which is how much the plant grows each day. Did the multiplication incorrectly. But their answer is a general result. So it's basically over any 2.5 day interval, the plant should grow 5 centimeters or 5 inches. They have 3 there, but this is representing over a general interval. Versus in the post-interview, the student did things a little differently. This is for the rainwater. They have to find how much rainwater in 3.5 hours. And we can just focus on this part here. So what they say is, the answer is 12 centimeters because 3.5 is in the middle of 3 hours and 4 hours. Or 3 hours measures at 10 and 4 hours measures at 14. And so then they're concluding in the rest of the sentence that between 10 and 14 is 12. In this case, they found the height of the rainwater at hour 3.5, so at a very specific interval. So students either did this, or sometimes they would find it at a specific interval, like 3.5 hours after the last part of the picture. So in this case, it's finding it at a specific interval. And we interpret this, before we interpret it, let me tell you what happened in the classrooms. So in this case, Henry's class, 13 students gave us a response that we were able to tell if something changed or not, and 21 for Anderson. So of those 13, 7 of Henry's students changed from finding a specific answer at a specific time to finding an answer over a general interval of time. For Henry, and then for Anderson, it was 5 out of the 21 that changed from a specific finding for a specific time versus a general interval of time. But then again, there were some students who went the other way around. And in this case, Henry's class, there was a smaller group that went the other way, but for Anderson's class, there are actually more students who went the other way. So we saw it as a distinction between the two classes versus the other finding, the same kind of effect happened for both classes. So now getting to what I was going to say before about the inner interpretation. We think that going from a specific interval or specific time value to a general interval is a possible indication of going from an action view to a process view. Because with an action view, you're thinking about finding a specific calculation, versus a process view, you're thinking more holistically about the function, and so you're thinking, you may be thinking that over any interval of time, say 2.5 days, that this is going to be the same over, it doesn't, I don't have to necessarily calculate it. I know that over any 2.5 day interval that this amount of change in height would occur. And we think the reason why Miss Henry had students going from specific to general more was possibly because she emphasized graphs a lot more, and she would discuss the shapes, the more holistic characteristics of these functions. Versus Mr. Anderson had far fewer days on graphing, much more focused on solving. And with solving, you're always finding something specific. You're making a calculation and coming up with a specific answer. Okay, so in summary, both classes we think exhibited some productive changes. Some students would change in one way, and then there would be a smaller group that would change in another way. But overall, Miss Henry's class seemed to show more productive changes over these two findings, and we also have a third subclase that shows that as well. So there seems to be something in the way the teacher was teaching that could have contributed to those changes in ways of reasoning. And we also think that this suggests that these changes in ways in reasoning could occur in this action and process view distinction, that this is one of those potential ways of reasoning that's susceptible to backward transfer. Maybe I'll just stop with this slide here to give people a chance to respond. So we think this is significant because it shows what's happening in real classrooms. It gives an indication that if the teacher is not intending to promote a certain kind of backward transfer, probably what happens is there's a lot of mixed signals going on. So it suggests that that's one reason why we haven't really studied it this much. If you're not intentionally trying to cause an effect, probably you're going to get some students who are going to pick up on some things, some students are going to pick up on other things, and you're getting a lot of mixed effects as our results suggest. And also, like I said, we think that this action and process view distinction is a potential way of reasoning that we think might be worth examining more, because it seems like it's a susceptible way of reasoning. So maybe I'll stop there. It's 11:45, and give people a chance to respond if you have questions. If anybody, I'm always curious if anybody's had backward transfer experience themselves, where you're teaching or where you were learning mathematics. I'd be interested in hearing that as well, but I'll open up the floor to whoever wants to make a comment or.
Can you turn back to the page where you showed two different ways of understanding the second question?
Two different ways of understanding what?
The second question, the growth.
The second question.
So, this page. So my question is like, why the post-interview way is a more holistic understanding? Because personally, I would do the way on the left, which I believe is like, I can understand this because I personally see it doesn't matter which place you're in the equation, the interval of increase is always 2.5 times 2. I mean, like this method, though appears to be with that action, students can still have a holistic understanding under that. And the right way just seems to be confusing to me. What's that?
Yes, no, you have the correct interpretation. This would be more of a process. We would think of this more as a process because this student is not finding the height change over a specific interval, but just over a general interval. This student here, this student was from Mr. Anderson's class, and more students started out with this kind of reasoning and went to the less sophisticated. This is not correct. This does not work for any 3.5 hour time. This only works at hour 3.5 because of the non-zero y-intercept. So you're absolutely right. This is more of we think this is more of an action view because this is only works at one place and it's a single calculation versus this represents any interval of 2.5 days. Does that make sense? So what you were I probably didn't say it correctly, but the way you interpreted it, your interpretation I agree with.
So in Anderson's class, more students go to the post way, which Anderson is the one who did more problem solving, right?
Did more solving.
Solving.
That's right. That's right. Does that answer your question?
Yeah.
Yes.
I'm wondering, what is the parameter to define, like, before and after, or conception and conception 1 and conception 2, like, what defines the proximity between concept 1 and concept 2? What makes concept 1 concept 1? Right?
Well, okay, so temporally, teaching concept 1 first before concept 2. That's what I defined temporally. Whichever one comes first would be concept 1.
The time-wise.
Time-wise. But as I also said, they should occur fairly close together. And so, I wouldn't expect that if you taught integer multiplication in grade 4 and then looked at circle equations in grade 9, that's going to be a backward transfer. That seems very far away. So I would think that they would occur very close together. But I'm thinking more about like topics. I mean, I'm using the word concept, but I'm thinking about topics that we normally teach in school, like where you have a unit on one thing and a unit on another as being fairly distinct units of study. And in there's concepts that the ways of reasoning about those concepts one might influence the other. Like differentiation and integration, they're like units in the course. And they happen temporally. Usually one happens before the other, although sometimes they might teach them in a more integrated way, which would be a different story.
Sort of related to my question is, with this criteria for backwards transfer, is it map domain specific? And what I mean by that, you have linear function, quadratic function. Those seem to be in the strand of like algebra function, because we have like algebra and geometry in terms of like being about transformations.
Absolutely. The broader you get, I think the harder the tracking kind of gets, because like if you're thinking about algebra versus geometry, like what specifically are you going to look at? You kind of have to pick something, because if you picked all of algebra, that would be hard to kind of connect that. But I definitely think that there could be connections between an algebraic approach to something and a geometric approach to something, and some transfer there for sure. Absolutely.
think you talked about, I think you made a hypothesis that, okay, you observed the shift from the pre-interview to the post-interview, and I think you kind of hypothesized that that may be due to the teacher's particular treatment, like different ways of treating the different, treating the quadratic, like how they teach the quadratic function. Do you have any evidence, like from the student's perspective, did you maybe ask them to reflect on what they did in the pre-interview, and then is that, I don't know, I'm just interested in the explanations for the shift, and then whether or not it has to be due to the instruction or maybe something else.
Okay, well, let me answer the first question first about the student's perspective. So what I've found, anytime that I've observed backward transfer, the students have not been aware of it. So we interviewed the students, the 4 students before, 8 students in all, but 4 students from each class. And when we asked them about their first response, and then asked them about their second response, they never said, well, I did this last time, and this time I'm thinking this. So that's one reason I think backward transfer is fascinating. I don't think of it as something that's necessarily, that they're necessarily aware of, like maybe they made an accommodation and they had this, all of a sudden they had a perturbation that led them to change their prior ways of reasoning. That's not what happens. Usually it's an unconscious change that they don't even realize that they made the change. And also when we interviewed the students, we interviewed them right after, so we didn't have time to look and see, what change, analyze the changes. If we had time, then we could have maybe said, last time you did this and this time you did this. Could you tell us why? So that would be actually a nice bit of data that would answer some of those questions. But unfortunately, we interviewed them and we just asked them, what did they do? And then the second part was, is there other explanations? Is that right?
Yeah, I'm just curious about
Well, I mean, one of the things I think that someone might say is that the students learn from the first assessment, and now they're based on what they learned, maybe they did something differently on the post-assessment. And I mean, that's possible, although we didn't grade the students and give them any feedback or tell them anything. So it's hard to know if they actually learned something. And it was also quite 4 to 5 weeks apart. I don't think most students actually remember what was on the pre-assessment versus the post-assessment. So that would be one possible alternate explanation. Another one would be that maybe they went to tutoring at night and they received some other instruction that we don't know about. I don't think that's the case because these students were low-income students, so they don't have a lot of resources. Do you have any other theories or?
No, I was just wondering, if okay, we observe this shift, this new kinds of understanding, or maybe is it stable enough? If we gave them another situation, maybe they go back to the previous one. I just.
Yes.
So, thinking about if there's any fundamental shift in a student's understanding of this content that it's stable.
So maybe the students, it's kind of a little more random.
Mm-hmm.
So if you had a question that was true or false, then I would take that. I would think more that student might, if they don't know what they're doing, they might one day say true, one day say false. But we were asking them to explain, so there's a little more reasoning going on there, and usually the reasoning is not that random. But Anna, what were you going to say?
So I think related to this, did you notice any correlation between which problem they did and whether or not they did what you're calling an action or a process view of the function? Because maybe a plant growing is different from rainfall.
We did do an analysis of patterns in the versions, and we didn't see any for these findings, but we did definitely see and I still can't understand why, but another problem that's not presented here, where we gave students, one context was where you earned money, and it was in tabular form, and the other one was in a tabular form too, but it was about megabytes of storage or something. I can't remember what the context was. But students did use one approach for the wage problem and the other approach for the megabytes of storage. Like, didn't matter where, if you gave it first or second. Now, I still can't figure out why, but that was a clear version effect. But in these tasks, there was no version effect. Didn't matter what version you had first. It was more of a trend going one way than the other.
So you said the first teacher who had some positive effects had focused more on graphing and factoring as opposed to solutions. When she was focusing on graphing, I'm wondering, were those primarily provided graphs to the students, or were they having to create their own? And do you think the difference in that would have an impact?
They definitely had to create their own. It was graphing with the purpose of them graphing. So they were like figuring out what the axis of symmetry was, what was the vertex, where were the roots, where was, we use the line of symmetry to draw half the line, half the graph, and then just fill in the other half of the graph. So spending more time holistically looking at the shape of the graph, students producing it, finding the critical points and using that to draw the graph. Versus Mr. Anderson did that just kind of briefly, one class, and then that kind of was it for the graph. So perhaps that I think of it as a little more holistic, gives people more of a process view of functions. Yes?
I was thinking about a lot of backward transfer that occurs in our teacher prep class, like in Dr. Moore's class. Like, the trig functions aren't just SOHCAHTOA, or in our middle school course, we're like, oh, that's why heat change flow works. Like, we learned this before in this way, and now, okay. So it's pretty interesting. My question was about part of this subclaim as well, because one thing you've narrowed down to explain the change was related to instruction, what Sherry brought up in terms of being focused on graphing or solving. I'm wondering if in the initial comic strip that you presented, it was introduction of concept 2, but the way I interpreted the finding was it wasn't necessarily the introduction of concept 2, it's the way they did concept 2. Are those two tied together in your head, or are they distinct?
Yeah, I think I would more gravitate towards the way they address concept 2, not just the introduction. So, how they talked about it, like the entire unit. And yeah, in that way, maybe I should revise that introduction and really focus on how do you learn about concept 2. Because I think if you're introduced to something and that would change your ways of reasoning, I bet you it would be a very short change. It wouldn't be very stable. Like maybe just having done something once or very quickly, if you did something with concept 1 right after that, there might be an effect. But the more you deal with concept 2, the stronger the effect. That kind of. And the other thing you were saying about kind of having these epiphanies where you're studying something new and you're like, oh, that's what. I think that happens a lot once you get into, say, undergraduate or graduate level mathematics. You're much more reflective and metacognitive. So I think that happens a lot. You're like, wow, I never thought about this before in that way, and that kind of really makes me think about these ideas differently. Unfortunately, 9th graders don't usually have those kinds of thoughts yet, usually. But I think that could definitely happen a lot. In fact, in the calculus integration problem, there was a student who learned about integration and then was having a lot of trouble thinking about derivatives again. And she realized that she's like, I never knew this before. Like, why is this so confusing now? Now that I know about accumulation of functions, now it's really confusing me. Like, what is the derivative anyway? So I think once you get into higher levels, that definitely comes into play. It's a little bit after 12, so probably people have to get going. But thank you very much for having me. It's been great to meet you.